All right, thank you. Welcome to What Physicists Do. It's my great honor to introduce Dr. Kim Coble. She is from San Francisco State University, which she recently joined. She joined the faculty there after having left Chicago State University, where she was faculty. Before that, she was a postdoctoral fellow at a National Science Foundation postdoctoral fellow at the University of Chicago and at Adler Planetarium in a joint appointment. She had also been a postdoctoral fellow at UC Santa Barbara, so she's been out in California before joining San Francisco State. Her bachelor in physics and astronomy is from the University of Pennsylvania, and her PhD is at the University of Chicago, where we overlapped, and so I've known Kim for many years. Her interests include the cosmology, where she has done some wonderful work, but also physics and astronomy education research, I think, which will be the focus of the talk here today. She worked with our own chair of our department, Dr. Lynn Kaminsky, and Dr. Kaminsky's group on the Big Ideas in Cosmology online textbook, which I think will be a fair bit of what we hear about today. So let's all give a warm welcome to Dr. Kim Coble.
Thank you all for having me here today. This is really great, really satisfying to be able to talk about the work I've done, especially with folks here. I've been coming in the summers for a number of years to work with Lynn's group here, and these are the fruits of our labor. So I'm just going to be talking about one of our projects, but my research projects in general have the overarching theme of the importance of using real data and active learning in astronomy and physics curricula for undergraduates. So I'm going to talk about the big ideas in cosmology, but we also did a project here, me and Lynn and Kevin McLean and some others, with the Global Telescope Network. So as you guys know, GORT is one of the telescopes that you guys own, and it can be robotically controlled. And I have a neat project where students from elsewhere can propose to do observations with this telescope and peer review each other's work and get real data, just like real scientists. I also work with other curricula from other groups, either data that's already been taken or traveling to radio observatories with more advanced undergraduates. And there's also a strong focus in my work on inclusive astronomy and diverse physics learners. Chicago State University, where I was at for 12 years, is a minority serving institution on the Chicago South Side, so it's primarily African American students, and San Francisco State, I think, was just ranked the most diverse large institution in the country, so this is something that's very important to me. You might ask, why should people study cosmology? And I think one of my students put this best when she had gone through a lab where she calculated the age of the universe based on real data, and she said, wow, we can use numbers to answer deep questions. That's why we do this. I think cosmology gives us the big picture. It's the study of the universe as a whole, its content, its structure, how it changes over time, and the physics behind it. And that's the backdrop against everything, and we want to know how we fit in with that. You might also ask, why should we study student ideas about cosmology? And anytime students enter a course, they are not blank slates. They are bringing different mental representations, and that can affect their learning. And we need to know what students are thinking and where they are in order to take them to where we want them to be. And so this type of research was done years ago on sort of visual astronomy type things like seasons and moon phases, but our group really wanted to bring modern astronomy topics, things astronomers really work on these days, as opposed to things that were known hundreds of years ago, into the curriculum. So there was very little of this that had been done when we started our project. And so there have been all these amazing new cosmological observations, advances in computation and visualization, where the scientific knowledge of cosmology has gone from fairly abstract and theoretical to extremely precise observational measurements, and not a lot of that has gotten into the classroom or had gotten into the classroom. When I was working on some cosmological science stuff and doing press releases, I got a real lesson in how necessary it was to bridge that gap. And so I was really happy to work with the group here on two things: research on student understanding of cosmology, and then developing a series of interactive web modules based on that. And I think it's really important to have both of those pieces, a strong grounding in the science and a strong grounding in pedagogy, and how they mix together, and how they mix together with the context of the student learning. So these are all of our collaborators, myself and my students, and then some of my other students from other places, and then of course the group here, which has, like I said, been really amazing to work with. And then Janelle Bailey, who is at Temple, who is the president of the American Association of Physics Teachers. And of course we have to thank our funding agencies, especially NASA. So there are a few key things that we think everybody should know about the universe: how things are structured, what the universe is made of, that it's not just the same matter that we're made of, but there's also dark matter and dark energy, and how the universe changes over time, and that this occurs not just randomly, but because of the laws of physics, and there are empirical measurements that we can make about this. So what we know and how we know it. So the curriculum that we developed, and if you'd like to know more, we have some nice flyers from the publisher up here. It has ways to log in to the curriculum. It's informed by a multitude of data on student ideas about cosmology. So we have pre-instructional surveys that we did with more than 1,000 students, where we asked them open-ended questions to get out all of their ideas. We didn't want to do a multiple choice where we presume to know what they were thinking. So then we code that with an iterative procedure so the students' voices pop out. We also followed up with interviews at Chicago State to see if people were saying the same thing as in the surveys, but just more in depth. We also looked at course artifacts like homework essays, lab warm-ups, exams, and so on. This was all before we built the curriculum, because we didn't want to just make stuff up. We wanted it to be based on where the students are. So the areas we've targeted so far, we have papers on the structure and distances, the composition, which includes where did the chemical elements come from, dark matter, dark energy, a lot of work on the expansion of the universe, the age of the universe, the Big Bang, and also on the fate of the universe and the curvature of the universe. And students often brought up how important it was to them to interactively engage with real data. And the context matters, so we wanted to engage this at diverse types of institutions. And so we did our surveys on different types of places. So, we had research universities, state colleges, liberal arts colleges, community college, minority serving, and even a religious college, because we wanted to get a wide range. We want to make sure these materials are going to work for everyone and that we're capturing everyone's ideas, not just one particular population. One of the things we did sometimes with a pre-instruction survey, but especially when we evaluated the effectiveness of the curriculum once we built it, was we also did coding for correctness. So something could be totally correct but missing some things, which would be incomplete. Could be partially, which is, they say, some right stuff and some wrong stuff. Could be wrong, could be no response. Could be true but irrelevant, or it could be non-scientific, non-serious response. These are the modules. It's broken up into 17 different chapters. This is a screenshot of our website. And instructors can mix and match these. So the first couple of chapters are things that are taught in most introductory astronomy classes. We've got a bunch of stuff on relativity. And we've got sort of the history of the universe stuff there to wrap up. So depending on what type of course you want, you can mix and match the different chapters, and the publisher has structured it such that you don't have to pay for the whole thing, you just pay for the chapters you use. The pedagogical approach that we take in each of the sections, it's much more interactive than typical curricula, where you read a book, and then you go over here and you do some homework. Here we have it interspersed throughout. So at the beginning of a chapter, we'll have a video that gets you excited about the topic. Then we'll have a warm-up dialogue where we take real student quotes from the interviews to elicit student ideas, to get your ideas out there, because it will sink in more when you read it if you think about it first. And then we've got some of the typical text, animations, figures, that kind of thing. And then we have these interactive tasks interspersed so that you hit a topic in a bunch of different ways, with reading about it, with numerical problems, with conceptual problems, and so on. And then in every chapter we have activities with real data, because as you'll see from the research, this was really important to learning cosmology. Okay, so I'm going to give you just a couple of topics. I'm going to show you the research that we did before we built this curriculum, surveying students about their ideas. Then I'm going to show you the curriculum, what we developed to address these ideas. And then I'm going to show you the evaluation of that curriculum and how well it seems to be working. So one of the big ideas that we wanted to start with is the structure of the universe. But people should know that the universe is made up of galaxies, which is made up of solar systems. When we surveyed students, a typical thing was for students to confuse the solar system and the galaxy and to say things like, well, a solar system contains stars and planets and stuff. A galaxy contains stars and planets and stuff. That's not wrong. We call that incomplete because that's not all there is that they could say there. Particularly difficult was the hierarchical nature of the relationship. Interviews were also confirming this kind of idea of just sort of swirly things and not really understanding how the structures fit in with each other. So here's a student quote going in depth on interviews. I kind of thought the galaxy was the universe, and the universe was something they just talked about, constellations. I didn't know, I just thought it was referring to stars or something. So, when people look at pictures, astronomical pictures, they're just seeing a swirly kaleidoscope of colors and shapes and not knowing how all of those things fit together. One of the things we saw towards the end of a course where we had a lot of work on students understanding structure throughout the semester, their understanding did become fairly robust. They definitely got the idea that the universe is made out of galaxies and the galaxies made out of solar systems and other things. The two things that were difficult for students were moving beyond the solar system being the sun and planets. A lot of people described, well, I made these styrofoam balls of the planets in elementary school, and that really stuck with me, but it was hard to go beyond that in terms of asteroids and comets and moons and really getting a full description of the solar system. And with the galaxy, there were a lot of pictures of where you just see the stars in the galaxy, so you just see the central bulge and you see the disk. The students had a hard time depicting a dark matter halo, which is a circular halo all around the visible parts of the galaxy. So we started bringing in that idea earlier and often in the class whenever we could, as we saw this in the research, and it actually really helped a lot. with students understanding that dark matter component and where it is. So in the curriculum, on our first chapter on the structure, where we sort of get down the basics of what is a solar system, what is a galaxy, how do they fit together, we start off with this what do you think sort of warm-up question at the beginning, where we have students choose if they agree with one of these students, and if so, whom. And it doesn't matter at this point. You're just trying to get your ideas out. So you get graded based on whether you did it, not if you did it correctly or not. And these quotes all come from real quotes from our research. So we have Annie saying a solar system has different things in it, like galaxies and planets and stars and stuff like that. Our solar system has the planets, Mercury, Venus, Earth, and so on. The planets have moons, so I think moons too. Brenda says, I disagree. I think a galaxy has stars inside it, and each one of the stars has planets orbiting around it, and that's what a solar system is. So a galaxy has solar systems in it, but a solar system doesn't have galaxies in it. And then Charles says something that a lot of students say, which are, I think the terms solar system and galaxy mean the same thing. And so if you are a student and you're reading through these choices, you might see something that resonates for you, and you note that down and explain your reasoning. And then if you read something that confirms that or denies that, then you can work with that material, because it will sink in more in your head than if you just go and read it. So we have some interactive tasks where you have drag and drop. So for example, in this one, you can decide which objects are inside the solar system, which objects are outside the solar system but inside the galaxy, which objects are outside the galaxy and inside the universe. And then you just drag and drop on the website into where you think they should go. Or you can rank objects by size and distances. And we have a number of these tasks to iterate on these concepts. And you do them right as you're reading, as you're going through, so you can test yourself right away. So, a lot of times you'll read a textbook and you'll think you understand it, and then 4 days later you go to do the homework and you don't understand it. Here you can work with it right away until you know you got it. One of the things we saw from the research happening is that even if students can get the relative hierarchical nature of things, they can't necessarily match that up with absolute numbers. And this is part of a thing from learning theory. It happens anytime you're working with very large or very small numbers in the geosciences, nanosciences literature. You see this effect where someone can do it like this student did on an exam. These two questions are on the same page of the same exam. On this one, the student gives a great explanation of the universe being made of galaxies and the galaxy being made up of solar systems. But over here, they contradict themselves by saying the size of the observable universe is smaller than any of the solar system or the galaxies. So matching absolute numbers to relative numbers is something that's difficult. So you want to, and that's been shown generally in the education research. So we have an activity with a powers of 10 tool where you can kind of go on a scavenger hunt and find absolute and relative distances to things so that you can see how those match up. Sort of working out from the more familiar out to bigger distances and then down to smaller distances. And each one of our chapters has a lab-like part that's called a wrapping it up, and a lab report-like thing called a mission report. Remember, we had NASA funding for it, so it's called a mission report, not a lab report. These activities typically work with real data or at least numbers. In terms of implications for student ideas and the teaching of the hierarchical nature of the structure of the universe, one thing is, this is something you want to hit as a theme throughout the semester. If you do that, students really get it robustly by the end. A lot of the upper elementary and middle school astronomy standards are around, the math standards are around this relative and absolute scale thing, proportions, stuff like that. And you can expand out to galaxy. You don't need it to just be solar system and planets with middle school students. And you can do it with relative scales. You don't need to bring in the most difficult parts, but I really feel strongly that students should be doing more than just the styrofoam ball thing with planets, especially because that brings together all of the STEM standards. Okay, so we did a preliminary evaluation of this. So we did the research where we got an idea of how students understand the structure and distances in the universe. Then we built the curriculum, and then we tested it. So we took some general education astronomy classes at a state university. We had a traditional lecture taught by one lecturer. We had a traditional lecture taught by a second instructor. And then that same instructor taught a flipped classroom using the modules. There are about 80 to 100 students in each of these classes. And we did a bunch of assessments in terms of typical attitude and content assessments that were multiple choice that have been done in the community. What I'm going to show you is the open response content surveys where we ask them to explain what's a galaxy, what's a solar system, and what's the relationship among them. And these are the results. It's a little difficult to read. On the horizontal axis, what we have is, well, first of all, this is section 1. This was a lecture. This is section 2. This was a lecture. This is section 3. This is a flipped classroom, but the same instructor as this one. This is correct. This is incomplete. This is wrong. This is no response. So, and this is pre minus post. So it's really good if it's taller over here and negative over here. What we see with the lecture class is, and I should also mention that this goes up to a bigger height. This is 150, this is 150, this is 150. So these gains, not too much with the lectures here. In this class, the one that used the modules, we see fewer people are wrong, fewer people are leaving it blank, and more people are giving a strong response or a correct response as opposed to the weak, the solar system has stars, the galaxy has stars kind of response. So here, this seems to be saying, and especially because these are the same professor, it's not like, you know, one professor being better than the other, really seems to be the style. Using the modules and working interactively with it seems to be giving students better content gains. Okay, one of the big things we wanted to address was math skills. No matter where you teach, no matter where you are at any grade level or any institution, you always wish your students were better at math than they are. But these skills are really important STEM skills to learn for life and for, you know, becoming a teacher or especially if you want to go into a STEM field. These include things like graph reading and proportional reasoning. And they come up in a variety of situations. So the types of problems we had were like, what if you travel at half of the speed of light? What about the inverse square law? Using rotation curves of spiral galaxies to reason towards why there's dark matter. One of the things we see is that with continual practice, students improve on these tasks. If you have the same sort of format over and over again, students can improve. So I'll give you one example, which is the inverse square law with distances. So, you know, the inverse square law says if things are the same luminosity, if they're the same inherent brightness, if they're farther away, they look dimmer, and it goes as an inverse square. Coming in, only a third of students know how to do this, given the equation, and answering things like this. You know, if star A is 3 times further away, that means it's going to be 3 times dimmer. If it's 3 times closer, it's going to be 9 times brighter. Students will mess up both of these. They'll get the brighter or dimmer wrong. They'll also get the square part wrong. But we see, as we worked with this concept in a consistent way throughout the semester, they did better on a midterm, and they did even better on a final. So with consistent scaffolding and support, you can bring the students to where you need them to be. So whenever we introduce math in our modules, we explain the equations in words. We explain them conceptually and proportionately. We have a step-by-step process for numerical problem solving. So as an example, we would give the inverse square law, that how bright something looks, how bright it inherently is, divided by distance squared. And we practice this in a bunch of different ways. So we have some conceptual multiple choice questions. We have a thing here where they have to measure and graph how bright the brightness is versus distance. And then we have some activities you can pick and choose from that use real data to find the distances to real astronomical objects. You know, we took in Hubble data and so on, so that students could get their hands on the real data. Okay. One of the other things we wanted to talk about are things that sometimes touch people emotionally. You see things like this in the national news, like what is the age of the universe? One of the things we wanted to ask people is not just what is the age of the universe, but how do we know? When we ask them what is the age of the universe, well, first of all, we would ask if it has an age or if it's always existed. That response that says no response or contradiction, a contradiction would be someone saying, the universe has always existed because it's 1 million or 1 trillion years old. Really? Yes, 15%. But I'm actually not too worried about this. So, okay, so people are coming into taking an astronomy class because they don't know. So people are kind of saying, like, I don't know, or they're saying it's really, really old. We didn't see any differences in our samples. Even sampling at a religious college, we have less than 3% of people saying that it's thousands of years old. These are pre-instruction surveys. They're not for credit. Comes up in interviews. This is what students are saying. They're saying it's really old. That's great. And they'll learn how old in their class. When we say how do we know the age of the universe, the most popular response besides I don't know is it's not possible to know. As a scientist who has measured the age of the universe, this hurts me. This hurts me bad. Because we have measured this. We've measured it to high precision from many different types of experiments, and that knowledge has not yet filtered out into the general knowledge. Another popular response is, how do we know that number? Well, my teacher told me, or I read it somewhere, or, you know, my friend on the street told me, and all of those things are the same thing, by the way. Like some sort of authority figure told me. And then we have about a quarter of people giving either, you know, reasonable, but maybe not right responses to this. Here's a classic example of a student who's confused about what we can and can't do with cosmological measurements. So they answer this question: the universe's age is infinity. It's been around longer than us and the dinosaurs. There isn't a way to tell except for scientific hypothesis, but those are not completely based on facts and real evidence. We saw this. Well, yeah, so there's a problem with understanding the nature of science here too, right? But for this particular example, it was really important for students to get their hands on the real data. So both for the age of the universe and the Big Bang model, people are coming in thinking there's no evidence, not knowing what the evidence is, stuff like that. These are some interviews that were done after students measured the age of the universe by doing a Hubble Law lab with real data. And here's what they say. So one of the students said, actually, when you told me, so this was at first just in lecture, I was less inclined to believe it, the age of the universe that you told me, to tell you the truth. I really didn't understand. At first I thought a lot of scientists kind of sometimes make up facts. I never understood it, so I thought a lot of stuff was made up. Now I do understand it, now that I saw the calculations and did them myself. Another student said, and people ask me, are you sure your students are being honest with you in interviews? I think they are. So another student who is now a teacher said, you know, we did this during the lab, which was awesome. We took pictures of galaxies and we measured them and we recorded them on graphs and came up with real authentic data from real galaxies. It was really real authentic information, so I got a lot from that. And so the fact that this was real data was extremely important to these students. So you may understand it conceptually, you may be able to regurgitate a number, but to really believe it down deep, students are telling us they need to work with the data. So we have an app for that. So in our cosmology modules, you can go through and measure the sizes of large spiral galaxies. If they're all inherently the same size, if they're farther away, they look smaller, and if they're closer by, they look bigger, and we can measure that and calculate their distances. We can measure their speeds based on the Doppler shift. And then you can put this together to make a Hubble diagram, which gives you the expansion rate of the universe, which then gives you the age of the universe. And students can measure how much wiggle room is there on that number. They can get the uncertainties on that too. And like I said, they say it's very valuable to do those measurements. So we had a preliminary evaluation. At the time that we did the evaluation, the Hubble Law Lab had not been made yet when we did our evaluation. So the students learned this concept through lecture. So prior to instruction, students had a hard time answering the why questions or the how do we know questions. Oops, I just told you it was done here. So all three of the classes who participated in this study did this by lecture. So it was the same sections, 1, 2, and 3, but in this case, 3 did not use the modules. They just used a lecture, and they get the same gains as the other sections. So I think this is sort of hinting that when section 3 did use the modules, they made much bigger gains. So again, this is telling us it's not the instructor, it is actually working with the data that makes the difference. Okay, the last big thing I'm going to talk about is the Big Bang Theory. Our warm-up questions come from a lot of, again, from the interviews and from the surveys. One of the things we see a lot of in the Big Bang Theory is students saying, giving an explanation of the Big Bang Theory that is not correct and then saying they don't believe it. So, you know, when you read about these things in the news where people say, you know, X many % of people don't believe the Big Bang Theory, they don't believe the thing that they think the Big Bang Theory is. So here's what they think it is. 50% of people, and other groups have measured this number also and gotten consistent results, think the Big Bang describes an explosion of matter outward like a bomb from some central point. People also describe it as the formation of the universe, the solar system, sometimes the Earth. Of course, we know people in the beginning are confused about what's the difference between the solar system and the universe. So it might be from that, but it might be that they really think it was something related to Earth. And when we ask how do we know, what's the evidence for the Big Bang? And again, there are thousands of cosmologists employed in answering this question. Again, there is no evidence for it. I don't know. My teacher told me. And only 14% actually know what the actual evidence is for the Big Bang Theory, which is seeing the expansion of space due to galaxies moving away from each other. So in interviews, we went more in depth. And what we saw in the interviews is students, even after they learned that the Big Bang wasn't an explosion, they were telling us that I really need a better visual to replace this. Like, I know it's not an explosion, but I still have that picture in my head, and that's such a good picture. You really need to make something to replace that. So the students are saying, I always heard about the Big Bang Theory and how it was this big explosion and how the planets and everything came to be. I don't really remember what it was that we learned in class, but I know I was told otherwise. I need some kind of visual to explain it to me. I have a thing like a stretchy band, which is the fabric of space. It's a physical therapy band with galaxies stapled on. And we call it kind of, one of my students named the Big Bang, the big stretch. And they like that visual. And we have a movie of that in our modules. But we also have an activity where they go through and they run an animation. So they've got a grid here. The grid represents the fabric of space. And these dots represent pieces of matter. And one way you run the animation, the dots all move out from a central place across the grid. And in an expansion model, the grid spaces themselves expand and the dots go along for the ride. And the students have to answer multiple choice questions about which one of these visualizations is showing an explosion, which one is showing an expansion, which one of these is the correct model for how the universe is actually working. So that they have to come to have the visual for expansion in their head and then know that describes reality. And then we go from there to build what that means in terms of how the universe changes over time. So we have a bunch of visualizations. With our visualizations, we always have follow-up questions because novices see visualizations differently than experts do. Not our group, but another person, Zoe Buck, found that if you have simulations of how dark matter grows, if you color the dark matter dark, the students know where the dark matter is. If you color it something else, like blue, like scientists often color things, all kinds of colors to mean different things. If you color the dark matter something other than a dark color, students will think that the dark matter is located in places that haven't been surveyed, or places of galactic voids, as opposed to places where the dark matter actually is. So we compare computer models and data. For those that know the cosmic microwave background, one of the things you can do is compare models and data to get the curvature of the universe. So we have a slider where you can try different models and see which model best fits the data. We have a bunch of stuff like that. Non-science majors are not going to, we explain what this graph is in terms of the cosmic microwave background. Really, they can just tell it's some kind of graph and they can tell that they're doing model fitting. Physics majors can actually understand what the graph means, but all of the students can get the idea that we have real precise data and only some parameters fit that, and that's how we know what the cosmological parameters are. Really fun game we have for the early universe is a particle game where you have neutrons here in white and protons here in brown, and you have to click on them to build up the elements, and you have 4 minutes, just like the universe had in the beginning. And if they're close enough and the combination works, it'll make that element. If they're too far away, it won't work. If you have a combination that won't build in real life, it won't build in the game. You have photons flying around that can sometimes hit your particles and dissociate them. So it's got all of the real physics in there, but it's super fun. And I have students like on different screens in the classroom playing this and getting real competitive about who can make the most lithium and stuff like that. So it's really fun, and it's a great visual. Okay, so I've shown you a couple of the topics that we've looked at. We've looked at structure, we've looked at how we treat the mathematics, we've looked at how we treat the age and the Big Bang. We've got a lot of other data out there that I haven't showed you, like the fate, the geometry, the composition, various things. We also want to extend this to future work where we do a bigger scale evaluation, where we take more than just a few classes. Maybe we want to make a quicker way of judging, student gains. I know the group here has done similar curricula, like taken the relativity section and really gone wild with that in terms of LIGO stuff with community college professors and professional development. The group here does a lot of amazing teacher professional development. I've got a bunch of data on what students think about black holes that I want someone to analyze. So that's sort of where we're going with it in the future. So to sum up, we know what we know about the universe because we have data. We know what students know about the universe because we have data. And students have stressed to us over and over again the importance of using real data in science and the active learning process, especially for topics like cosmology that seem abstract and out there, but which really come down to earth when you work with it. All right, so thanks, and any questions?
We have a nice time before 5 o'clock for our questions, so let's begin.
And you guys can also ask me about GTN stuff if you want. Yeah.
Just 100 years ago, there were plenty of prominent scientists who thought that there was no difference between the galaxy and the universe, and that the age of the universe was something that could not possibly be determined. 100 years from now, it may turn out the universe has been infinite all along. Just the current expansion began a little less than 14 billion years ago. Can you talk at all about the history and how these things were discovered?
Yeah, so so the person who's the expert on putting the history of all this into the modules is Kevin McGlynn, and he does go into the history of that. One of the things that really strikes a lot of my students who are maybe religious in background is finding out that the Big Bang Theory was developed by a Catholic priest, for example, and they get very interested in those sort of connotations. I think the thing that is really super important is not just what we know. I don't want them to just memorize some number and then forget it. I want them to know how we know, right? So the tools and measurements and understanding uncertainty and precision and all of those things in the scientific process are what we really want them to take away. And so, you have to know science, you have to do science, and if it's a general education class, a lot of people are going to not become practicing scientists, but they're going to read stuff about science in the news, and they have to know what it is that scientists really do, that we don't just make stuff up. And so, what it was in the past, what it is now, what it is in the future, has that context of science does change, but there's some things that we know really, really well and are going to have to be incorporated into any future work. We have really, really precise measurements, and you have to be able to explain those. Yeah.
So how do you choose what questions to put on your website? Like, how do you know what students will be able to learn on their own?
Yeah, so this is not on their own. So this is always facilitated as part of a course. And so we've taught it a couple different ways. I taught it as purely an online class. I taught it in a lab class where students were working in groups. It's been taught in a flipped classroom where students did it at home and discussed it in class. So it's always facilitated by a professor. So the professor chooses which content they're going to do and how they're going to work with the students. So I like to have some of it, the way the work has worked best for me of all the ways I've tried it, is to have some of it in the classroom and some of it at home, have sort of the harder stuff going on in the classroom working in groups, and some of the easier stuff at home. We tried to scaffold the curriculum so that students could make pretty decent progress on their own to figure out, that's part of the research into, which things are really hard to learn and which things are easier to learn and how much scaffolding do we need to put in there.
I had a question about that hierarchy. I think my first thing is that I feel like that's an important thing to bring. A lot of the textbooks sort of talk, and it's phenomenological, these things exist, but this sense of hierarchy. So tell me about how the activities help them get that sense of scale of hierarchy, because you know, it's still all just a mixture of words and meanings to them. And what kind of activities do you have to help people see this is constrained to a solar system, and this is a galaxy?
So we have ranking tasks, like the ones I showed you, where you have to put the objects in order by size, by distance, by whether they're in the solar system, galaxy, and universe. We have one where we have a picture of the galaxy, and we have like different dots marked A, B, C, D, E, like where might a nebula be? Where might something in our solar system be? Where might, you know, the nearest star be on a picture of the galaxy? Another thing is you can kind of carry this throughout the semester. So students are coming in with some idea that there are planets and stars and stuff. They know there are objects out there, and so they're not coming in with nothing. You can build off of the fact that they have probably heard these object names. They just don't have a framework for how they all fit together. Because when you you go and look at something online, it's pretty pictures, lots of pretty pictures. And so we want them to put that into a coherent whole. And this is something that they can really robustly get by the end. One of the things we saw was like with dark matter, which is something students don't know about. I started teaching that class with just, they didn't know what dark matter was. And we did like one day on here's how we know there's dark matter. And students came away with there's dark matter, but they had no idea like what it was they did because they were unfamiliar with it coming in. So you can leverage the students' strengths of knowing that there are these objects out there, even if they don't know all of them, and work with, putting them into a framework so that they can incorporate more things. And let's see, what other activities do we have? Yeah.
Well, I probably should ask separately, but it was old chapter 12, so whatever we did was 12 too, and we have the SDSS one where we're magnetizing bubbles. How well does that one actually work for students?
That one's been tricky. So we have one chapter that's on the large-scale structure of the universe. So here they're working with galaxies and clusters of galaxies and larger things. And one of the ranking tasks we had, so the ranking tasks that go like size and distance, students get that piece of cake. Here we decided to rank on volume, where you have things that are like, you have filaments that are one-dimensional, you have walls that are two-dimensional, and you have voids that are sort of three-dimensional. And those things are all sort of the same size across, but they're different volumes. And that isn't working as well, because the students just read a ranking task and they want to put them all as the same. So
that plotting thing that rotates, but still it's hard to see.
yeah, so one of the things with large-scale structure was it was especially important for students to understand what they're looking at. So when you're dealing with solar system or a picture of the galaxy or something, the things that students have seen pictures of before, they can then pretty easily put them into categories. Things that students haven't seen pictures of before, like galaxy surveys. You need to do more scaffolding. So we have like questions about large-scale structure surveys of like, what do the dots mean? Okay, those are the galaxies. And we have questions about like, what are the totally blank areas? Okay, those are places that haven't been surveyed, because the students definitely don't know that because they're unfamiliar with that.
How much internal linking is there between the different modules, and is there any linking to outside?
So the modules, I mean, you could do them all in order, but they can stand alone so that you can buy them separately. So as long as the instructor has given the students the background they need to do stuff, like let's say you're doing a class for physics majors on relativity, you could just use the relativity chapters. Or an advanced cosmology class, you can jump right into the cosmology stuff if they already know what the galaxy and solar system are. And so each one of those can stand alone. There are some concepts that cut across, and we have links to boxes that'll pop up, but there aren't a ton of those. And links to outside, we have some links to outside, and especially We brought in a lot of data from outside, so we have a lot of credits, but one of the things that happens when you link to outside is somebody else has to maintain it, and then sometimes it breaks. And so we ended up developing more of our stuff than we initially thought we might, just because we didn't want it to break and then not be able to do anything about it. Yeah. And then the Hubble, the Space Telescope, had this amazing app for like the orbits around black holes, and it broke, and they didn't give us we were like, we'll fix it if you give us the code, and we couldn't get a hold of the code, so that was kind of sad.
I don't know, this Wes was searching and went through and found all the links in every
Yeah.
single chapter. He went through it explicitly in spreadsheet.
Yep. There is an amazing amount of debugging that goes into something like this.
Well, it's a long project. It took like more than 5 years, and
Yeah.
we're still fixing it.
Yeah.
Well, of course, then you discover something like gravitational waves, and you have to.
That's the cool kind of fixing it, right?
You have to update some chapters.
Mhm.
You did very quickly. That was fun.
Well, I know I have a few more questions, but I feel like they're of technical nature, and so I think some of us would like to stay for some further discussion of a technical nature, but for the rest of you, if you have no further questions, please leave quickly and quietly, and the rest of us will continue